So this lesson is going to be a fun one. We're looking at rotational volume again, but a different perspective on how to create the volume formula. Personally, I prefer the cylindrical shell method to the disc washer method. And part of the reason I prefer it is because when you're using the washer method, you have to have two area formulas subtracting from each other to subtract out an excess that was created. With the shell method, it never creates excess. What it does is, I'm having lag time again. Come on. Okay, I don't know what's wrong with this, but anyway. So if I were rotating about the y-axis, when I'm using the disc method, I would have radii that are perpendicular to that axis, and I would have horizontal rectangles. With the shell method, I take vertical rectangles right exactly where the region sits, and each rectangle holds its distance to the axis of rotation and floats around and creates a nice little cylinder. And when you're using the shell method, it's called the shell method, but it's cylindrical shells. You always draw your rectangle parashell to the axis of rotation. Ha 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 ha. So when you're using the disc method, the rectangles are perpendicular to the axis of rotation. When you're using the shell method, the rectangles are parashell to the axis of rotation. Ha 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 ha. Now, I found a couple of things to help you visualize what is going on beyond just these pictures. And let's see, this is one of them. So it's showing in red a sample cylindrical shell. The dark blue is showing just the region on an XY plane. And then in green, you can see the rotation of the full creature. So there's that one. And then I found this other thing. It's definitely old. You can tell it's old. And so it shows it's about to restart. There we go. The top one just restarted. So it shows a purple section on the XY plane. And then it's drawing sample vertical rectangles. And then it's halfway rotating so that you can see it a little bit better. And then it finishes up to a full rotation and slowly brings each shell in. So these actually look a lot like the nesting dolls. If you know what I mean, those little nesting dolls, pop it open. Oh, there's another one. Oh, there's another one. Some people like to do that with boxes for gifts. Maybe it's just my family, but apparently it's funny, especially when the center box is empty. My brother did that to me once. He thought it was just hilarious. Then they wonder why I had issues. Anyway, sorry. That was too much information. Or when they zip tie it. Oh no. Each zip tie is so hard to get off. Oh no. Yes. Yes. And my son's favorite is to completely duct tape. Completely. Yes, it's all part of the fun. That's right. Okay. So True, true. It's fun for them. All right. Now, I don't know why this keeps like doing this. There we go. So if you take one of these shells that you get, and it's basically like if you peel the label off a can. When you peel the label off, you end up with a rectangle. And the height of the cylinder is the height of this rectangle. So this is showing that f of x is the height, and f of x is the height over here. The circumference creates the other dimension of the rectangle, and the circumference, you know, is 2 pi r. In this particular situation, the rectangle is actually an x distance from its axis of rotation. And I'm going to go into more detail on that. But basically, you have 2 pi r times h, and then you multiply it by tiny little delta x if it's a vertical rectangle. If it's horizontal rectangle, then it's the delta y. So I'm going to add a little bit to this formula right here. And with the circumference, I'm going to say that it is 2 pi times a radius function with respect to the x variable. And with the height functions, it's not necessarily f of x. When you're looking at the height, I'm going to start off by saying h of x for height with respect to x, where it is often a top function minus a bottom function. So f of x minus g of x, this particular situation has g of x being equal to 0. So it's not written. And that's because the region that they are showing you is attached all the way down to the axis of rotation. So because of that, the height of the rectangle is the f of x function minus 0. But what you also are going to want to draw, because the axis of rotation is not always going to be the y-axis. If you put like a dot on your rectangle and then make a segment go over to the axis of rotation, that is your radius. And what you want to realize is when you set up an integral from a to b with respect to x, that means from x equals a to x equals b, whatever formula you have going on in here, the x variable is going to go through every single real number in here. Tick, 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 tick. Plug it in, add. Plug it in, add. Plug it in, add. Tick, 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 tick. So as you are moving along the x-axis, the actual location of that rectangle is the x variable of the integral, whatever x variable it's on at that particular moment. And technically, the axis of rotation is at x equals 0. So we end up just writing x times f of x with the 2 pi, but there's a little more to it than that. And I'll make sure to go over problems to show you different situations. So we'll start off with example 1, and there's a pretty picture to go along with it. Find the volume of the solid obtained by rotating about the y-axis. The region bounded by y equals 2x minus x cubed, which includes this is part of that curve, and it's also bounded by y equals 0. And if you solve for the intersection points, you're going to take that 2x squared minus x cubed, set it equal to 0. And you should be able to see that it only intersects the x-axis at 0 and 2. And if I were to actually draw out that whole thing, it would look about like this. But when I look at, yes, it does look like a bundt cake. In fact, we should, like, with the metal shop, make functions and then have them create things. And we can do a calculus metal shop combo. Anyway, so we've got this region is bounded by y equals 0 and this curve, and that pushes that it is just this section. So what I'm going to do is I'm going to draw a sample rectangle. And then I'm going to draw a little radius over to the axis of rotation. And by the way, when I drew that blue rectangle, I was thinking parashell to the axis of rotation. So I've got radius and height. Then the formula is 2 pi r h for the integrand. With the rectangle being vertical in its length, that means horizontal is what's cut up into tiny pieces, and it's a dx integral. I need to know the x coordinates where the region exists, and that would be 0 to 2. And now all I have left is to set up a formula with respect to x for the radius and the height. Keep in mind, again, that I am going to go through every real number for x from 0 to 2. So this integral is going to go tick, 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 and an x is plugged in to the integrand, a calculation is made and written down. The 2 pi comes from the fact that it is, this is the circumference, so it's 2 pi r for the one of the dimensions of the rectangle. And I call it a peeled off label from a can. So x is going through all of these numbers. When I look at this blue rectangle, it's on some specific x coordinate, somewhere between 0 and 2. The radius is the right x minus the left x. The right x is the actual variable of this integral. The left x is 0, which you don't have to write minus 0. Then the height of the cylinder is a vertical length. That means I need the y top minus the y bottom. And we've been doing that for all of the problems beginning with area. So just keep in mind that this part is the part you've been doing every single time. The top y value is 2x minus x cubed, or 2x squared minus x cubed. And the bottom y value is 0, which again, you don't have to write the minus 0. And that gives you a nice little integral that you can then integrate on your own. And I'm just going to clean it up a little bit. And remind you that before you solve the integral, you have to distribute the multiplication over that subtraction. Then you're ready to go with the power rule, and bam, you'll get a number. All right. I'm moving on to a next example. Yes, yes.
I'm curious on how you get x for the radius. Do you just like pick just whatever the variable is?
Well, the thing is, you know that for the horizontal length, you need whatever x is on the right minus whatever x is on the left. The weird part is that the x coordinate on the right happens to actually be the variable location. It's literally just as I go from 0 to 2, at some point I'm going to hit x equals 1/2. And when x equals 1/2, the distance to the axis of rotation is 1/2. When x is 1, the distance to the axis of rotation is 1. When x is 3/2, the distance to the axis of rotation is 3/2. So the actual x variable itself is the distance to that axis of rotation.
Okay, that makes total sense.
Excellent. So this is an example of when I'm rotating about the y-axis. The next example is going to rotate about the x-axis. Come on, wake up. There we go. So rotating about the x-axis, we have a region formed by y equals the square root of x. And let's see, also bounded by the x-axis. And then it says from x equals 0 to 1. So we get that region. Now, if the x-axis is my axis of rotation, then when I draw my rectangle, it is parallel to the axis of rotation. And if I have a rectangle that is horizontal, then vertical creates the tiny cuts. So I'm dealing with a dy integral. I need to know the y coordinates where it exists. And for this particular function, when x is 1, y is 1. And now I'm ready for the area formula for the integrand. If I'm using cylindrical shells, then the area formula is 2 pi r h. The distance to the axis of rotation is a vertical distance. With a dy integral, it's going to go through all the real numbers for y, 0 to 1. Tick, 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 tick. And at any one moment that I stop and let the integral go through the calculation, I'm at some particular y. And that y is the variable of the integrand because it's a dy. And so if you can kind of picture these rectangles just floating up through, and they are actually at a y location. So this vertical distance is the y variable itself minus 0. And it's okay if you write just y, but I want to always emphasize that every time we find a length, it's a subtraction of two numbers. It's between 2 points. Then for the height of the cylinder, that's the same as the length of the I'm all twisted. My cord twisted around me and I couldn't move. Never mind. For the height of the cylinder, I am looking at the length of the rectangle. With it being a horizontal length, I need the right X and no, I don't answer the phone. Okay. I need the right X minus the left X. The right X coordinate is 1, but for the left X, it is following this curve, but I need to know what X is equal to for that curve. And so when I square both sides, I get that X is equal to Y squared. So Y squared is the X coordinate of the left side of that length. And then I can clean it up a little bit, but I'm not going to go through the full integration. Once you get to this point, it's just a matter of using the distributive property and then power ruling through. Yeah. The height is basically that same height that we had for when we were doing just area. It's the same height that we used for the radius of the disk method. And it's the same height that we used in the cross sections that were creating a particular side of a shape. So we are now going to look at some problems where the axis of rotation is not the X or the Y axis. Now, when you hit homework problems that start with number 15, that's when you stop using the X-axis or the Y-axis for the axis of rotation. With this problem, it says that we are using the region bounded by y equals x to the fourth, y equals 0, and x equals 1. So you can see that along here, y equals 0, y equals 1 gives us this region. And we are rotating it about x equals 2. So now when I draw my rectangle, I want to draw it parallel to the axis of rotation. And I'm going to get some of this excess out. And you'll find your own way of what order you want to do things in. I'm going to stop there and start talking about the formula being 2 pi RH. The integral is going to be a dx integral because the height of the cylinder is a vertical dimension. That means the cuts are tiny horizontals. I need to know the x coordinates where the region exists. So that would be 0 to 1. The height of the cylinder is what I'm familiar with. Top y value minus bottom y value. The top y value is x to the fourth. Bottom is 0. The only thing that's new and kind of awkward is how to set up the formula for the radius. Because you have to realize that the variable is x for this integral. When you draw your rectangle, if it's a vertical rectangle, then it gets a width through a tiny horizontal pop. If you have a horizontal rectangle, then it gets its other dimension by popping out in the vertical direction. So when I'm looking at the length of this radius, I want to realize that x is going to be the variable from 0 to 1. So at any given moment, the x coordinate where I draw that vertical rectangle, that is the x variable of the integral. And if I want to find this horizontal distance, I need to look at the right x minus the left x. The right x is 2 minus the left x is the x variable itself. And once you get comfortable with the shell method, a lot of people tend to prefer it. But it's nice to be able to have a couple different ways to approach a problem. Okay, one more example. Oh, yes, absolutely. With these problems, they just add another way that you can do rotational volume, which is why technically the shell method isn't on the AP test, but that doesn't mean you can't use it. What that means is in the multiple choice category, if you're looking at a bunch of integrals to choose from with rotational volume, they used the disk washers to create those formulas. But other than that, if you're just coming up with an answer, you can use any technique you want, even though it's not technically one of the things stated to learn for the AP exam. You can still use it. All right, so this time I'm looking at a region bounded by this equation, which is a hyperbola, this vertical line, and that gives us what I just shaded in yellow. And we are rotating about the line y equals 5. So we're going about a horizontal axis of rotation. So when I draw my rectangle, it's going to be parallel to the axis of rotation. Once I draw the rectangle, the differential is going to be the other direction. So if this is a horizontal length, then the differential is a tiny vertical cut, and it's a dy. So I need to know the y coordinates that this exists between. So basically take the intersection between those two and plug 4 into x. You'll get 16 minus y squared equals 7. And subtract the 7, you'll get 9. So plus or minus 3. Then the area formula for your cylindrical shell, 2 pi r h. And I'm going to start with h because we're familiar with it. To find the length, I need the right x minus the left x. The right x is 4 minus the left x. I have to isolate the x variable for this formula. So I'm going to add y squared to the right and then take the square root. When I square root, I do get plus or minus, but we are using the section where x is positive, not the section where x is negative. So it is the positive root, not the negative. So that gives me then that the right x is the square root of 7 plus y squared. And then finally for the radius, I can take any point on that rectangle and draw a radius over to the axis of rotation. And that is a vertical distance. So I need to know what is the top y, what is the bottom y. The top y is 5. The bottom y is whatever y coordinate I have stopped at to calculate the formula. So it's the y variable itself. And I feel like the shell method also really helps to instill a bit more what's going on with the formulas as we use them. And so that is the shell method. Now, what is going on for the remainder of today and tomorrow? You have a last homework assignment for a while. I'm going to go over questions you have for cross-sectional volume, and then we'll take a quiz on cross-sectional volume today. Tomorrow, I'll go over some AP problems so that you can see some full free response problems that involve area volume. They're very, very common. And you will turn them in at the end of class and go. So I'm not going to give you homework to procrastinate on. Cross-sectional volume is in the textbook. I just gave problems differently on a worksheet because the textbook's cross-sectional volume problems are actually hard to read. And people struggle more with reading them. And so I just finally stopped assigning them. We'll do a quiz on average value, and you can see there won't be a quiz on the cylindrical shells. I'm just going to not do a quiz on cylindrical shells because it is technically not on the AP exam, but I think it is good for you to learn. And you can always use it if you need to. When we get back from break, we will review a bit before taking a test. And I have to decide when I want that test to be. How much review do we need? I don't know. Anyway, so let's now look at, let me stay with it and focus. Do you have questions from these cross-sectional volume problems? Going over one or two right now would be helpful for you to prep for right before taking the quiz. So, do you have anything in particular? While you think, I can show you that I went over these two problems with period 1. So while I'm waiting for a number, I can at least talk to you about these problems. Also, I want to warn you on the quiz, I do have both perpendicular to the x-axis and perpendicular to the y-axis, so make sure you read that carefully. Number 3 is perpendicular to the y-axis, so you can see the rectangle that is horizontal. And if that rectangle is horizontal, then the other dimension, the vertical, is the tiny cut up piece. And the y is going from 0 to 1 for the region. Then, and you know, if I tell you you can't have formulas in front of you for the quiz, then the only people not using formulas will be the honest people. So you can have those formulas in front of you. Just understand that you need to have them memorized for the AP exam if you are going to take the AP exam. So equilateral triangle, area formula is root 3 over 4 times length of side squared. And then to get the length of that side, I'm looking at the length of the rectangle, which is horizontal, so the right x minus the left x. The right x is 1. The left x comes from y equals x cubed, but I have to isolate that x to make it cube root of y, and that's what the left x is equal to, based on if I'm located at that particular y level. And then I also went over with them number 5, and since so far I see number 3 has been asked for, I'll just go ahead and keep going with that. No. Okay. So with this one, you have the graph of y equals 2 to the x. And where do exponential functions cross the y-axis? The exponential functions cross the y-axis at y equals 1. Now, when you go to graph y equals 1 over x plus 1, you want to realize that that's the graph of y equals 1 over x moved left 1 unit. So you know that the graph of y equals 1 over x has asymptotes for the x and the y-axis. You also know that it goes through 1, 1, and -1, -1. If you move everything left 1 unit, this point is going to move over to the y-axis, and that's where they intersect each other. So through this problem, I want you to see that sometimes you can find intersection points better by drawing the graphs, because if you had to solve that algebra without a calculator, that would just not be pretty at all. So that gives us this intersection point. And then we are told that the region is also bounded by x equals 2. And so that gives us what I have colored in yellow to be the only enclosed section. So for this one, it's a little bit strangely worded, but one of the things is you've got to figure out what is on the XY plane for this rectangle length. What side of this two-dimensional object is there? So it says, for this solid, cross-sections are rectangles with length perpendicular to the x-axis on the solid's base. So on the solid's base is what has been given to you as length. And then the width, which sounds a bit odd to use, but keep in mind with rectangles, we tend to interchange. In fact, we interchange a lot of things in area formulas. That's why a lot of times people use altitude instead of height for triangles, to emphasize, altitude. But it's just about the orientation of the object. And if the orientation changes and we keep using the same words, it's confusing. But you've got that this is on the base, and the other dimension is twice as long as that length. So I've got L and 2L giving me an area formula of 2L squared. And so I get 2 length squared. Then when I go for the length, I realize that I have a top y and a bottom y. For the top y, it follows 2 to the x. The bottom y follows the 1 over x plus 1. And, remember, with cross-sectional volume, which is what you're quizzing on right now, it's not rotational volume. With cross-sectional volume, you have an area formula for a shape on a plane, and that plane is not on the xy plane. It is orthogonal or perpendicular to the xy plane. So you're coming up with an area formula for a shape that is not on this two-dimensional plane that you see here on this xy plane. It's basically popping out of your screen and coming toward you for the other dimension of the rectangle. You have to figure out the area formula of the shape that is told to you. And after the break, when we're reviewing for the test, I'm going to talk to you about the fact that you don't have to know the shape. You just have to know the area formula. So there are some interesting problems that I'll show you after the break. But for the quiz today, it's just purely focused on traditional problems where you are told a particular two-dimensional shape, enough information for you to come up with an area formula for that two-dimensional shape. So it's a geometry formula. And we're not doing rotations. So when you are told that the cross-section is perpendicular to the x-axis, you will draw in only the region of vertical line segment. If you were told that the cross sections are perpendicular to the y-axis, you would need to draw rectangles that are horizontal just in that region. And these lengths are creating one side of a two-dimensional shape. And from that one side, we have an area formula for that two-dimensional shape. For the moment, I'm going to not answer questions about rotational volume because you're mixing it up. And I can talk about it more tomorrow and then when we get back from break also. But I want to focus you on right now that we're not dealing with rotational volume on this quiz. You are just finding the geometry area formula, which you should have in your notes. And then it's either a right x minus a left x or a top y minus a bottom y for the length of one side of that area formula. All right. So are you guys ready? I'm going to